In this video, I want to talk about the power rule. That is, I want to come up with a formula that will help me take the derivative of x raised to some power. So I have three examples here I just want to go through and see if we can see a general pattern that's occurring so that if the exponent were something more complicated than a 2, 3, or 4, we could take the derivative easily. So I'll just start with x squared. All right, so let's see. I have x plus h all squared will go here. And I'm just going to go on and multiply that out. Minus f of x, which is just x squared, all over h. I see that the x squareds will cancel. And then there's a power of h to cancel out of each of those terms. As h goes to 0, I see that my derivative of x squared is 2 times x. Let's see if we can do the same thing for x cubed. And I would see that I have an x plus h cubed minus x cubed all over h. And now what I need to do is expand the x plus h cubed. And I could just say x plus h times x plus h and then distribute again and write that out. The same kind of way I guess I was thinking about that, but I want to show y'all a quicker way of doing that arithmetic. What I have on this board is known as Pascal's triangle, named for the French mathematician Blaise Pascal. Pascal's triangle always starts with a 1 on the top. The ends of each row are always a 1. And then after I have the 1, 1, and 1, I generate the next row by starting with a 1 and then adding two terms together and ending with a 1. So 1 and 1 make 2 in the middle there. So 1, 1 and 2 make 3, 2 and 1 make 3, 1. I'm going to add another row. Start with a 1, 1 and 3 make 4, 3 and 3 make 6, 3 and 1 make 4, and then end on a 1. And just one more row, just for the heck of it. And we could extend Pascal's triangle as far as we wanted to forever and ever. One of the neat things about Pascal's triangle is that the rows actually tell me the coefficients for when I square what we call a binomial, a polynomial with two terms. And I said square there because I'm thinking about this row, but it actually would help us raise a binomial to any power. So x squared plus 2xh plus h squared. 1 times x squared, 2x times h plus h squared. So I see the 1, the 2, and the 1. If I look at the powers of x, they count down. I have x to the second, x to the first, and then x to the 0 here, right? There is no x. The powers of h count up. H to the 0, h to the first, h squared. And that's how I can use Pascal's triangle to square a binomial. This row will help me with cubing a binomial. The coefficients will be 1, 3, 3, 1. I start with x to the third. All right, and now the powers of x will count down, and the powers of h will count up. So my coefficient's a 3. X squared times h plus 3 xh squared plus h cubed. In each term, the exponents on my two variables add up to the power I'm raising it to. So 3, 2 and 1 make 3, 2 and 1 make 3, and 3. And this first one, all of them sum to 2. 1 and 1 make 2, and I actually see the squares on those two. All right, so let's do x plus h to the fourth. And that's going to be an x to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. All right. These are the ones I needed for the problems on that other board, but I'd like you to pause the video. And just for fun, use Pascal's triangle to find x plus h to the fifth. All right, so I'm hoping that you had paused the video and had written that out. I'll write it out so you see the final answer. I have x to the fifth plus 5, x to the fourth h plus 10 x cubed h squared plus 10 x squared h cubed plus 5 x h to the fourth plus h to the fourth. And now I could actually imagine continuing to use Pascal's triangle to keep being able to raise a binomial to higher and higher powers. All right, so let's go back and find the derivative of x cubed and then x to the fourth. So now what I know is that x plus h all cubed there is the same thing as what I had written on that other board, which I've set off to the side and out of the frame of the video, but it was x cubed plus 3x squared h plus 3x h squared plus h cubed minus, so that's that part. Now I'm just ready for that minus x cubed. And again, the x cubes cancel. And what I see going on here is the power of x will always be the first thing and the thing I write that I'm subtracting off, so they'll always cancel. Everything else will always have an h in it because those h's powers are counting up. So I'll have a 3x squared, the h would cancel, 3xh plus h squared. And I really think I see what's going on now. I'll always be able to cancel off an h. This first term that didn't subtract off will always be an h to the first. So that will completely cancel and I'll have that. Everything else will have at least an h to the first in it. So when h goes to 0, I just get what was my second term. All right, and I think I'm starting to see a pattern. This was an x to the third and I see a 3. And it's being raised to the second power. This was an x squared, its derivative is a 2x to the first. I think even if I stopped here, you could write down the rule that should go here. If that was an x to the n, I think you could go on and fill in the blank. I'm going to do one more example, but if you're feeling really bold, go on and write down what you think the power rule is going to say. All right, so now I need x plus h to the fourth minus x to the fourth. So we found x plus h to the fourth on my other board, so I'm just going to write it down. X to the fourth plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth minus x to the fourth, all over h. And again, the x to the fourth terms will cancel. I'll lose one power of h in all of these. So that will be a 4x cubed after I cancel the h. Everything else will still have an h in it. So I'll just get 4x cubed. And I think the power rule says this, that I have n times x raised to the n minus first power. That what was the exponent is now a coefficient, and the exponent went down by 1. That anytime I have x to the nth power, I should be able to easily find its derivative. All right, so let me write down the power rule. And I'm going to then talk about why that's true in general by using Pascal's triangle. All right, the derivative of x raised to the n power is n x to the n minus 1. Well, if I look at Pascal's triangle, let's see. This row tells me the coefficients if I have a square term, the coefficients if I have a cube, a fourth, and a fifth. And if I go backwards, this really does tell me x plus h to the first coefficients, because that's just x plus h. And this row really does tell me x plus h to the 0, because anything to the 0 power is 1, as long as both of those things aren't 0. All right, so Pascal's triangle does always summarize the coefficients all the way down. And 1, 1, 1, since I'm adding two terms, that's a 2. And then this row all the way down will always give me that second term, what becomes the coefficient in my derivative. And I'm always getting it by adding 1. Well, that was a 2, so the next one's a 3, a 4, a 5, and that'll keep going on and be true forever. So that second term where that coefficient will come from, because it has an h to the first power, will always be n. Because in the nth row, this is the 0th row, the first, the second, the third, I will always have n as the second thing. Well, that does a good job of telling you why the power rule is true in the case of a whole number. The power rule is actually more powerful than that. This rule is true for any exponent where the values of x to the n and x to the n minus 1 are defined. So it's actually a very powerful rule for any number, even though the justification we kind of just talked about was only for whole numbers. So the generalized power rule says that if I take derivatives of x raised to a number, I know that's going to be this. So x to the 100, the derivative is 100x to the 99th. And I could continue doing that. The derivative of x to the 75th power is 75x to the 74th. I really don't want to use my definition of limit to take this derivative, but using this rule we've just talked about is very easy. Let's talk about the derivative of the square root of x. Well, if I remember that the square root of x is x to the 1/2, then the power rule would say its derivative is 1/2 times x, and then 1/2 minus 1 would be minus 1/2, which would be this, which would be 1/2 square root of x. And that makes me very happy because we've taken this derivative before using the definition, and this rule matches what we got there. One more example for now. The derivative of x to the pi is pi x to the pi minus 1. I'm not going to round anything. I'm just going to leave it right like that because exact answers are always preferable. That's the power rule.